welcome to Chem 112. Today I'll be going over the prerequisite material review. This is topics from Gen Chem 1 or Chem 110 that will be pertinent in Chem 112. So a lot of this is periodic trends, acid-base chemistry, and electrochemistry. So why don't we start? We're going to begin with the periodic table because, this is chemistry. The periodic table's just a tad important. We can start with periodic trends, but before we hop into periodic trends, why don't we discuss why the periodic table is colored the way it is? So there are 3 different colors on this table, and this is to indicate the different blocks. First, we have the S block, which encompasses the alkali and alkaline earth metals, and there are 2 columns here. Then we have the D block, which is our transition metals, and there are 10 columns. And we have the P block, which are the noble gases, nonmetals, metalloids, and post-transition metals. With helium chilling up here. That's part of the S block. Anyways, the P block has 6 columns. So why don't we see how this relates back to the electron configurations of atoms and ions? We're going to begin with sodium, and sodium is an atom that is in the S block, so this indicates that whatever the electron configuration we get for it should end in that S valence. And according to the periodic table, sodium is going to have 11 electrons, and the way we fill this in is, remember, we're going to have a spin up and a spin down, and we fill them all in first one way and then go in the other way. So we're just going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So according to this then, our electron configuration for sodium would be 1s2, 2s2, 2p6, 3s1. And if we look back at our periodic table, sodium so happens to be in the first column and the third row. So right around here. And that's kind of interesting because if we look at its valence shell, we can see that it's a 3s1. Now what happens when we have the sodium cation? This means it's positively charged, so we're going to remove 1 electron, meaning it's going to have 10 electrons, and we're going to remove what's the easiest, which is this 3s electron right here. So we're just going to get rid of it, and this gives us a new electron configuration of 1s2, 2s2, 2p6. And if we notice something interesting, we have this 2s2, 2p6. This electron configuration is known as the noble gas electronic configuration, and it's really, really stable. It has this full valence. Our sodium cation is more stable than sodium as its atom. And this makes sense because we know that our alkali metals like to be positively charged. Now why don't we look at chlorine? Chlorine is in the p block, so this indicates that its electron configuration should end in the p valence. And it has 17 electrons. So similarly, we're just going to go through and fill them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. Thus, its electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p5. And similarly, if we look at our periodic table, chlorine's going to fall in that 5th column in the 3rd row, so right around here-ish. And looking at its electron configuration, it's a 3p5 configuration. Now, if we have a chlorine anion, that means it's negatively charged and it has an additional electron. So it's going to have 18 electrons. And to illustrate this, all we need to do is add 1 more electron right over here. And this gives us a new electron configuration of 1s2, 2s2, 2p6, 3s2, and 3p6. And once again, we have this noble gas electronic configuration. So this chlorine anion is much more stable than the chlorine atom, which again makes sense. This is a halogen. It likes to be negatively charged. And the last one we're going to look at is a transition metal, iron. So iron is, I believe, number 6 here. And we're going to use the noble gas notation to help us. So here it's going to have a complete 4s orbital, and then we have 6 electrons. It's 3d orbital, so we'll start 1, 2, 3, 4, 5, and 6. This gives us an electron configuration of argon, 4s2, 3d6. Now, a lot of transition metals like to be positively charged cations, and a common oxidation state for iron is this positive 2. To get this positive 2, what we have to do is just remove the electrons from the 4s orbital. This is more easily accessible than the electrons in the 3d. And our electron configuration then becomes argon 3d6. Cool, right? Alright, why don't we discuss the trend for atomic radius? So an easy way to remember this is draw a little snowman right over here. We'll add some features onto him. What we can see is right down over here, it's really large, and up here is really small. What about if we look at it left to right? How does this look? Well, say our snowman falls over because we got some wind. That's wind coming in. We're going to have him all over the place, but the small pieces will be over here now and the large pieces over here. So our trend for atomic radius, I'm going to erase this, it increases as we're going to that bottom left corner. So we have really large radii for like francium and barium, but up here helium and fluorine both have really small atomic radii. What about the trend for electronegativity? Well, if we know anything about electronegativity, what we should remember is that fluorine is we should remember that fluorine is the most electronegative atom. So if we just draw an arrow to our fluorine, this is the trend for electronegativity, so it's opposite of the trend of atomic radius. We can also see similar trends when we're looking at items such as first ionization energy. So first ionization energy is the amount of energy required to remove an electron from an atom. So the lower the ionization energy, the easier it is to remove an electron. What we're going to see then is a very similar trend where the most electronegative atoms are really hard to remove electrons from. And that makes sense, right? They want to keep those electrons. The last trend that we can look at is the trend for electron affinity. So this means how much an atom wants to accept electrons. And the way the arrow is going to point is to the more negative values, because the more negative values indicate that they are more able to accept electrons. And similarly, it's going to point towards our fluorine. However, there are some exceptions to this. So when we're looking at the noble gases, we know our noble gases already have a stable octet. So they're actually going to have a positive electron affinity. They don't want to accept anymore. Noble gases. Alright, we've talked a lot about periodic trends. Why don't we talk a little bit about structure? Acid-base chemistry is a huge unit in this course, so it's important to understand how these structures look, as that'll help you identify acids versus bases. So before we get into that, we can discuss the general rule of thumb for how many bonds certain things that we see often like to make. Starting off with carbon, carbon likes to make 4 bonds to complete its octet, while nitrogen likes to make 3 bonds and oxygen likes to make 2 bonds. Now halogens we also can include, in which they only like to make 1 bond, and then they only like to make 1 bond, which will complete their octet. And hydrogen is one of the exceptions to this rule, where it doesn't need a complete octet, it only needs 2, so it only needs 1 bond. So why don't we draw some structures based off this information? If we begin with C2H6, what we can first deduce is that each carbon can have 3 hydrogens. So why don't we start off with drawing that? All our hydrogens then have enough bonds. However, our carbons are both missing one, so we're just going to connect them in the middle. For H3O+, we'll begin with drawing oxygen in the middle. Each hydrogen needs one bond, and we can connect them all to the centroid oxygen. What these wedges mean just dictate the orientation of which they're pointing, meaning one is pointing out of the page and one is pointing behind the page. And lastly, we need to throw on the lone pair for the oxygen, thus indicating this is positively charged. There are some exceptions to the octet rule, and we can see this with boron. So if we draw boron in the center, we can complete the octet for each fluorine atom. And each one of these will have 3 sets of lone pairs. However, if we look at our centroid boron, it doesn't have a complete octet, and that's okay. It is an exception to this octet rule. As we discussed earlier, nitrogen likes to have 3 bonds. This first way might not be too helpful in telling us what the structure looks like, but the second way it's written tells us a lot. So it's saying that we have a carbon with 3 hydrogens, as well as a nitrogen with 2 hydrogens. Now we know our nitrogen needs 3 bonds and our carbon needs 4 bonds, so we can connect these two. Additionally, our nitrogen's going to have its lone pair. And what we have here is what's known as an amine. Now these are really important functional groups that you have to make sure to draw out in this course because it changes their functionality if they're neutral, negative, or positively charged, and drawing out the Lewis structures helps identify the charge on that nitrogen. The next structure is CH2O. So don't get confused by this H2O. That doesn't mean that there's water in this with carbon floating around, because then carbon can't have its 4 bonds. We can begin with drawing our carbon in the center and connecting the 2 hydrogens to that. Now our carbon needs 2 more bonds. And we know oxygen also needs 2 bonds. And we can throw in the lone pairs, and here we can see everything has its complete octet with the exception to hydrogen. This can also be drawn like this, in which this little point right here just indicates a carbon. And the last structure they give us has 2 interesting functional groups to it. First, we see this COOH. Now, every time you see COOH, think carboxylic acid. So a carboxylic acid is going to have the structure like this, where this is just the carbon right here like we discussed earlier. Now the other important thing is the C6H5. So this is a really important moiety used quite frequently, and it's just benzene. So a benzene ring is just a hexagon, so 6 carbons that are fully conjugated, so we have this resonance going on in the middle. And each one of these carbons has a hydrogen sticking out because remember, carbons need 4 bonds, and if we take a look at like this corner, what we have is this carbon right here has 1, 2, 3, and then this hydrogen just which isn't explicitly drawn on the structure. Earlier we were dealing with some functional groups. Why don't we look a little deeper into those functional groups? First, we have a carboxylic acid. So a carboxylic acid has the COOH formula, and the way it is drawn is as such. This is the same thing. We can put an R group here. R group just means there's some other group there. It could be a hydrocarbon, could be a benzene ring. Another way that we can draw this, these are the same thing, but they'll be used interchangeably within this course. Amines are another important functional group we'll see throughout this course, particularly in acid-base chemistry, where it's really important to draw out their Lewis structures. So for a primary amine, it has a general structure of RNH2, where R can be any type of hydrocarbon, and from the previous example, what we saw was something similar to an ethylamine. There's also secondary and tertiary amines, which have generic structures like such. And lastly, we have alcohols. And alcohols take the general structure of ROH, and one we'll typically see and talk about is ethanol, which is commonly used as a solvent. This is it for the functional groups, as these are the three primary ones discussed in this course. Alrighty, let's move on to some reactions in acid-base chemistry. So the first one we're going to do is a strong acid and a strong base, and you do need to have these memorized for this course. So a good strong acid would be HCl, which is hydrochloric acid. So we're just going to write out the overall reaction right now, the molecular reaction. So we have HCl, which is aqueous. We're going to add some strong base to it. So a good one is sodium hydroxide. And from this, what we're going to get is water and a salt, sodium chloride to be specific. This is a neutralization reaction. It's a strong acid and a strong base. They're neutralizing each other. Now we're going to break this up into its full ionic reaction. So remember, strong electrolytes can be broken apart. So what we're going to see is we have H plus and Cl minus from our HCl. We'll additionally have Na plus and OH minus from our sodium hydroxide. And water will not break apart, so it'll stay. However, our salt will. So we'll get Na plus and Cl minus. So now we're just going to cancel out the things that are equivalent on both sides. So what we can see is that our Cl minuses cancel out and our Na pluses do. Now we can write our overall reaction. So we get H plus plus OH minus goes to H2O. Now how does this change when we have a weak acid and a strong base? So for a weak acid, we could use something such as acetic acid, which is C3COOH, and if you remember from earlier, the COOH is a carboxylic acid. And for our strong base, again, we'll just use this NaOH. And when these react, what we get is again water, because we're reacting an acid and a base, plus another salt. This time we have sodium acetate. And again, we're going to split this up into its full ionic equation. And since acetic acid isn't a strong electrolyte, it's going to stay as is. However, the sodium hydroxide will break into its ions. Sorry, these should say aqueous. Water will remain water, and our salt will break up. And once again, we'll just go through this and cancel out the similar things. So on both sides, we have a sodium ion, and that's the only thing that we can get rid of. So our net ionic equation ends up being acetic acid plus hydroxide goes to water plus acetate. So we can see how these two differ for a strong acid and a strong base versus a weak acid and a strong base. In this course, it is really important to be able to identify strong versus weak acids and bases. Enough of that, let's move on. All right, enough about acid-base chemistry. Why don't we talk about some dimensional analysis and stoichiometry? This will be important in this course as we're working with different conversion units, so we have to understand how our units cancel out. So what's illustrated here is the Haber process. You'll learn to love it by the end of this course. We'll use it a lot, and this is how we generate ammonia. So here, what we're going to do is we're going to consider a theoretical 200 milliliter reaction flask. Let me change this color. So a scientist has 28 grams of N2 in the aforementioned flask. What is the concentration of N2? So first we have to get moles because what it's asking for is concentration, and concentration is represented by big N, which equals moles per liter. We have the amount. We need to convert it into liters. So to do so, we can do 200 milliliters, and 1 liter is 1,000 milliliters, and this gives us 0.2 liters. And now we have to find moles. To find moles, we can take our grams, and then we're going to multiply by the molar mass, or I guess divide by the molar mass. But what we'll see is we'll have 1 mole of N2 on top, and nitrogen is 14 grams per mole. Since we have 2 of them, this is 28 grams per mole. Now this is the molar mass, not the weight of it. And this gives us 1 mole of N2. Thus our concentration is 1 divided by 0.2, giving us a 5 molar N2 solution. Now it's saying if all that N2 is used up, what is the concentration of NH3 produced? So for this, we're going to use the mole ratio. If we look at N2, it has a 1 in front of it. Well, not written in, but there is a 1 in front of it. And NH3 has a 2, so it is a 1 to 2 ratio. If I have 1 mole of N2, as stated from the previous problem, and I'm trying to convert to moles of NH3, I would have 2 moles of NH3 per 1 mole of N2. Now these cancel out, and I'm left with 2 moles of NH3 in the same reaction flask, so I still need to divide by that 0.2, which affords me a concentration of 10 molar NH3. Cool. Let's go on to the next problem. Alright, let's move on to enthalpy and thermodynamics. This is a huge unit in this course. We have a whole section just for thermodynamics, so it's really important that we understand the differences between enthalpy, entropy, and free energy. Today I'll just be going over enthalpy. So enthalpy, if we remember from Gen Chem 1, is the heat exchange with surroundings. So we can describe this in 2 different ways. A reaction can be exothermic or endothermic. For an exothermic reaction, this means that our enthalpy is negative. So temperature-wise, our surroundings are going to get hotter. Contrastly, for an endothermic reaction, this means that our enthalpy is positive and our surroundings are getting colder. So in Gen Chem 2, we really like diagrams and graphs because they're great ways to illustrate the concepts you've been learning. And I think this is also true when we're discussing enthalpy. So when we have an exothermic reaction, this means that our reactants are going to be higher in energy than our products. So our reactants are here and our products are here. Our delta H will be measured from our products to our reactants, thus being negative as our products are lower than our reactants. For an endothermic reaction, our reactants will be lower in energy than our products. Our delta H then will be positive as we're doing products minus reactants, and our products are now higher in enthalpy. So why don't we look at some problems that illustrate exothermic versus endothermic reactions? If you made it this far, here's a little bonus. My cat Vinyl decided to join. Let's see if you can hear her. Thank you, Vinyl. I'm sure they all very much enjoyed it. Alright, back to chemistry. So, why don't we move on to actually applying this in math and understanding how negative and positive enthalpies relate back to reactions? So, in order to calculate the enthalpy of a reaction, we like to use this products minus reactants rule where we take the enthalpies of formation, where we take the summation of the enthalpies of formation for the products minus the summation of the enthalpy of formations for the reactants. This just means we're going to add the enthalpies of formation of our products and then subtract that from the added enthalpies of formation of our reactants. And when we're reporting enthalpy, we want to report it in kilojoules. So it's important to notice in this table, they give us kilojoules per mole, so we need to cancel out the moles as we're going through. So a great reaction to begin with is the combustion of hydrogen gas, because often in this class we do like to combust hydrogen gas balloons. They're really fun and you'll see them a lot throughout the semester. So looking at this reaction at room temperature, what we're given is we have 2H2 plus O2 goes to 2H2O gas. So we're going to start off with our products, which is H2O gas. So we're going to be looking at this one. We don't care about this one right here. And since there's two of them, we're going to do 2 moles times its enthalpy of formation, which is negative 241.8 kilojoules per mole. And this is our only product, so this is all that we need here. Minus the summation of our reactants. So this will start off with our hydrogen gas, which is 2 moles, times its number, which as we see right here is 0. And we'll add that to the O2, which is 1 mole times 0 as well. And the first thing that we can notice is that our units are going to cancel for our moles. And what we'll end up with is a negative 483.6 kilojoule enthalpy. So this is a negative delta H, meaning it is exothermic. And this makes sense because if we think about what's going on, we're lighting a balloon on fire. Of course the temperatures of course the surrounding is going to get hotter. Now, how about photosynthesis? I'm certain we've all heard of photosynthesis. It's a really important reaction that stores energy in the form of sugar, so that's what this complicated looking molecule is down here. And it also produces oxygen. Similarly, we're going to go through it, and we'll start off with our sugar. So our sugar, there is 1 mole. We have 1 mole, and we'll multiply that by its standard enthalpy of formation, which is negative 1271 kilojoules per mole. And we need to add that to O2s. So we have 6 moles of that, and multiply that by that enthalpy. And we'll subtract our reactants from it. So we'll begin with water, and remember this is gas again, so we're going to use the same number we did up there. And we'll add that to our carbon dioxide, which has a number of negative 393.5 kilojoules per mole. And what we'll see again is that our units will cancel. And now we end up with a enthalpy of positive 2,540.8 kilojoules. So as we can see, this is a positive delta H, so our reaction is endothermic. So what this shows is for photosynthesis, we're having an endothermic reaction. Our reactants are lower in energy than our products. However, for the combustion of hydrogen gas, this is an exothermic reaction. So our reactants are higher in energy than our products. So why don't we move on to electrochemistry? Electrochemistry is a topic discussed later in the course of Gen Chem 2, so it's really important that we understand the difference between oxidation and reduction. And this is where oxidation numbers are really, really important, and we need to know how to assign them. So I have some general rules for oxidation states of what things typically like to be in. So things like alkali metals, so our group 1, these like to be positive 1, while our earth metals, group 2, like to be positive 2. We have halogens, so that second to last group right next to our noble gases, they like to be negative 1. Hydrogen typically likes to be positive 1, and oxygen likes to be negative 2. Now, there are some exceptions to this rule, and we'll see some of the exceptions in these examples, so let's just hop into it. We're going to start off with NO2. So when we start with these, we want to start with what's most electronegative because that takes priority, and in this case, it's going to be oxygen. So oxygen contributes a negative 2 charge, and we have 2 of them, which means its overall charge contribution is going to be negative 4, and this molecule has a 0 charge. So whatever our nitrogen is needs to balance this out, meaning it has to be positive 4. We can similarly apply this logic to NO3 minus, where oxygen again is contributing negative 2. However, we have 3 of them, so this is going to be a negative 6 contribution, and the charge of our molecule is negative 1. So our nitrogen needs to be positive 5 to balance this out. Now, what we have next is a little bit of a weird case where we're actually going to begin with our sodium. Our sodium is going to have a positive 1 charge per sodium ion, and there's 2 of them, so that's a positive 2 charge, and our overall complex is 0, meaning whatever our oxygens are contributing has to be negative 2. But we have 2 oxygens, so each oxygen is contributing a negative 1 charge. Now, this is one of the exceptions to when oxygen will be negative 2, and this is typically seen when we have peroxides. So, a peroxide is something that has this double bonded O in the middle. We have 2 covalently linked oxygens connected to some outer molecules, and in this case, what we're given is this sodium peroxide, which can be drawn like this, or more accurately, like this. So anytime we see a peroxide, those oxygens will have a negative 1 charge associated with them. They give us an iodine anion. So this one's actually really straightforward because it tells us the charge of it. It's just going to be negative 1, and we'll often see this happen with transition metals, where we'll be given a complex like Fe3+, its oxidation state then is just positive 3. Why don't we look at sulfuric acid? So sulfuric acid is a strong acid that you do need to know for this class. And to assign its oxidation state, we're going to begin off with the hydrogens and the oxygens. So we know each hydrogen is going to contribute a positive 1 charge, while each oxygen is going to contribute a negative 2 charge, and there's 4 and 2 of these respectively. So that means we have positive 2 minus negative 8 must equal 0, and to make this statement true, we need something to balance out this negative 6 charge, with a positive 6 charge. So while sulfur is directly under oxygen on the periodic table, it's not always going to be in that negative 2 oxidation state. It can be in examples such as H2S. What we're seeing here is an example of a positive 6 oxidation state instead. Thus, it's really important to go through these steps and assign oxidation states, as this is imperative when we're deciding what's being oxidized versus what's being reduced in a reaction. So, what does that mean then? Oxidized versus reduction? Well, if something is being oxidized, that means it's losing electrons. And an easy way I like to remember this is the oil rig mnemonic, where oil is oxidation is losing electrons. And since you're losing electrons, this means that the oxidation state is increasing. Conversely, reduction is gaining electrons. And another way to remember this is through the same mnemonic, combined it's oil rig, where rig is reduction is gaining. And consequently, the oxidation state is going to decrease. And then there's also terms oxidizing agent and reducing agent. So an oxidizing agent is just the species that is getting reduced. Meaning a reducing agent gets oxidized. So it's really important to pay attention what the question's asking for, and primarily pay attention to, are these words agent in them? If you see this, remember, think the opposite. So why don't we practice with identifying what's being oxidized versus what's being reduced given some reactions? So the first one, what we have is lithium and lead reacting together. And the first step always is assign the oxidation states. So since lithium is solid, it's going to be 0, while we have this lead cation that has a positive 2 charge. Now we have a lithium cation with a positive charge, and lead with a 0 charge because it's solid. We're going to begin by identifying what's getting oxidized. So if it's oxidized, it's losing electrons, so its oxidation state is going to increase. And if we look at our lithium, lithium is going from 0 to positive 1, which I would argue is an increase in oxidation number. Thus, lithium is getting oxidized, i.e., it is the reducing agent. Now we can move on to reduction, and remember, reduction is gaining electrons. So to gain electrons, its oxidation state will decrease. And looking at lead, we're going from positive 2 to 0, which again I would argue is a decrease in number. So our lead cation is getting reduced. Thus, it is the oxidizing agent. Now, why don't we look at chromium oxide and potassium permanganate reaction? This one is a little bit more involved because we need to go through and assign the oxidation states, which aren't as apparent. So again, we can start off using our rules. If we know oxygen is contributing -2, and there's 3 of them, this means an overall -6 contribution. To balance this out, we need chromium to be +6, but look, we have 2 chromiums. So each chromium is going to contribute a +3 charge. Now, looking at potassium permanganate, we have an alkali metal and oxygen. We know our alkali metal is going to contribute +1 and our oxygens are going to contribute -2. Since there's four of these, one potassium, this is going to be an overall -7 charge these two species are contributing. So manganese needs to be +7 to balance this out. And now if we look at our product side, we have this manganese oxide where oxygen contributes -2. There's two of them, so that is a -4 contribution. So manganese needs to be +4 to balance it. We have this potassium dichromate where our potassium is going to contribute +1. Our oxygens are going to contribute -2. This overall contribution ends up being a -12. And since we have two chromiums, each one's going to be +6 to balance this out. So now that we've assigned oxidation states, we can figure out what's being oxidized and reduced. We'll start off with oxidation, so it's losing electrons, its oxidation number is increasing. And the first thing that we can do is immediately rule out oxygens here and our potassium. And looking at chromium, we're going from +3 to +6, which I would argue is an increase in number. So our chromium oxide is being oxidized, thus is acting as the reducing agent. In particular, our chromium is what's being oxidized. And then if we're looking at reduction, we're looking for something that's gaining electrons, so its oxidation state is decreasing. And if we look at our manganese, it's going from +7 to +4, so that is being reduced. So KMnO4 is reduced, oxidizing agent. In particular, our manganese is what's getting reduced. As a side note, this is actually a really cool reaction because potassium permanganate, it's this purple complex, is a really, really useful oxidizing agent, especially in the oxidation of metals. And that is the end of the prerequisite material review. I hope this was helpful and a good refresher for a lot of those Gen Chem 1 topics that we'll be using in Gen Chem 2. Remember, if you have any questions, we have a wonderful online textbook that you can access and a wonderful instructional staff. The LAs, the TAs, and your professor are amazing resources if you have any questions. I look forward to an amazing semester of Gen Chem 2. And yeah, if you made it this far, here's Vinyl. She's been chilling with us today. You've probably heard her earlier in the video. Thank you so much for your kind attention and good luck in Gen Chem 2. You're going to do great.